Okay, so we'll now continue the uninformed search strategies which we were working on in the previous class. So we spoke about depth limited depth first search. So another variant of depth first search is what is called the iterative deepening depth first search. So what is done in the iterative deepening depth first search is that you keep increasing the depth limit. Okay, so you start with 0, then 1, then 2, etc. Okay, till the goal is found. So since we are not sure what would be the depth limit, what we are doing is we are keeping on increasing the depth limit. Okay, at one at a time. Okay, so we keep the depth limit as 0, then depth limit as 1, 2, etc. Okay, so this is the algorithm which is used. So what you are doing in depth limit is from depth of 0 to infinity, you keep on doing depth limited search, right, with the problem and the depth. So you keep increasing the depth, but as soon as you find a solution, you are going to come out. If result is not equal to cutoff, then return the result. Okay, so if result is got from this, then you are going to return the result. So this is your iterative deepening that is used. Okay. So what you find here is it combines benefits of depth first search and the breadth first search over here. So you find that like in the depth first search, the memory requirements is order of B to the BD, okay, where D is the depth up to which you go. Okay, so you are increasing the depth and depth limit, and when you reach a depth limit at which you are getting the solution, it may be say D, okay, then your memory requirements is order of B into D, okay, and like breadth first search, it is complete, okay, because you are keeping on increasing the depth limit. You find that it does everything from the shallowest level, and therefore it is complete just like the breadth first search. So you are able to get the optimal optimal solution. Okay. So here if we take this one, this shows you how the iterative deepening actually works. So here it's taking the limit as 0, so which means only the first node is there, that is the start node. Then when it takes limit as 1, it checks this node and this node, okay, and when it doesn't get a solution, it will change the limit to 2. So when you change the limit to 2, it's going to expand this, then it's going to come and expand this, okay, and check all these nodes. So all of these are all the nodes which are searched. Then it take depth limit as 3, okay. Similarly, you can continue with depth limit as 4, etc. And every time it chooses a node for expansion, it's going to check whether that is a solution, or I think, yeah, as soon as it expands a node and gets a new node, it checks whether that node is a goal state or not. If it is a goal state, then the solution is reached and you stop at that point, and you don't have to keep increasing the limit beyond that. Okay. Now you may think that this is a waste. This may seem wasteful because you are actually duplicating getting the states again and again, right? But what happens is that what we are duplicating is the nodes at the higher level. Okay, so there are not many nodes there. You find most of the nodes are at the depth D or whatever, right? At the lower levels, at the as D increases, you find that at the bottom level you find that most of the nodes are there. So at the upper level nodes are generated multiple times, but overall it does not give rise to so many nodes. Okay, so we can see here this gives the total number of nodes. Okay, so you find that the nodes at the bottom level, that is at depth D, they are expanded only once generally. Okay, and it goes backwards in that way. Okay, so here we can see that at the level at the bottommost level at level D, the number of nodes is b to the d, but it is generated only once. And if we go backwards, okay, the first level, you have b nodes and that is generated d times. Okay, then below that you have b squared nodes and it's generated d minus 1 times, etc. So in the iterative deepening method, this gives the total number of nodes that we have, right? And the time complexity of this is order of b to the d, okay, which is the same as the breadth first search. So let us look at an example here. So suppose you take b is equal to 10 and that is the branching factor is 10 and d is 5. Okay, so at level 5 you are finding a solution. So if I find the number of nodes using iterative deepening search and the breadth first search, this is the total number of nodes that you get. So you can see that iterative deepening search has a little more nodes, but not really that much as compared to the breadth first search. Okay, so you find that the iterative deepening method is the preferred search strategy when the search space is large and the depth of the solution is not known. Okay, then using the iterative deepening DFS makes sense basically. Okay, so this is what we get here. Okay, completeness, yes, just like the breadth first search. Time complexity, order of b to the d. Okay, and d is your lowest level at which a goal exists, and space complexity is order of d, which is really good basically. Okay, and optimality is there. So iterative deepening is a good option basically. Okay. Now the next search we are going to see is what is called the bidirectional search. So what you are trying to do basically is that you start from the start state and try to go forward towards the goal state, and you start from the goal state and try to go backwards towards the start state. Okay, and if the two searches can meet in the middle, okay, then you may get the solution much faster. Okay, so it would be something like this. So this is your goal state and this is your start state. Then if you come say till somewhere here and they are able to meet each other, then you can go from here backwards like this, and from here you can go backwards like this and able to find the entire path from here to here. So that's what we mean by bidirectional search, right? So what happens in bidirectional search is that the distance, I mean you are only going for d by 2 here, okay, and d by 2 there. So it will be d by 2, b to the d by 2 plus b to the d by 2, which is, that is the complexity here, okay, which is much less than b to the d. Okay, so bidirectional search will take less time than if you are doing the search only in one direction. Okay, but the problem with bidirectional search is it has to be done properly so that the two searches meet each other, right? Another so here they have taken b is equal to 10. Okay, if you take bidirectional search, you are getting 2220 nodes generated, and if you are using a breadth first search, this will be the total number of nodes generated. So the time complexity of bidirectional search is order of b to the d by 2, and space complexity is also order of b to the d by 2, which is much less than the breadth first search basically. Okay. So what happens is the frontier which you are getting when you are going forward and the frontier which you are getting when you are going backwards from the goal state, you have to check if there is any node which is common between the two frontiers. And as soon as you find that there is some nodes which are common between the two, it means that you have reached a point where you can combine the two paths, okay, to get the overall path. The problem is that searching backwards may not be always possible. Okay, so there are some types of search where searching backwards is the same as searching forward. Okay, for example, in the 8 puzzle, etc., then it may be able to use the bidirectional search. But in some cases, for example, if you take the n queens problem, it's not possible to go backwards from the goal state because we don't know the goal state, right? So it's difficult to use bidirectional search in such cases. So what you find is that bidirectional search works only in some types of problems, it won't work in all types of problems. Okay, so this actually compares the different uninformed search strategies. Complete except for the depth search, okay, you find that the breadth first search, uniform cost strategy and others like that are complete. Okay, depth first search is not really complete. If you take time complexity, you find that the time complexity is like this. Bidirectional search has a little less complexity, and here it depends on L and M, etc. And this D actually may be much smaller than the D which you get when you're just using depth first search, right? So that is the thing. The space complexity, we can see that depth first search and depth limited search has a small space complexity as compared to things like breadth first search, right? Also iterative deepening also has a good space complexity, right? Optimal except for depth first search, the rest are optimal, right? Okay, now that we have considered some search strategies, here we are using actually OR graphs, okay. So we are saying either if you start from the, say from the start state, we are saying you need to go either to one state or to the other state or to the third state, right? But in some cases you may, it has to be, it could be that you need to do both, okay. So suppose I start from the start state, I can say I have to go to A and I have to go from the start state to B, okay, only then I get the solution. So these are what are known as the AND graphs. So you have a mixture of AND and OR combined together to form the AND OR graphs. So what happens here is they are what are called hypergraphs. A hypergraph will have, say, if you consider a node can have more than one element connected to it. Okay, so the second element could be a subset of elements. Okay, and it may be necessary to go through all those elements. Okay, so hyperarc are also called what are called K connectors. Okay, where you say if K is equal to 1, we get OR nodes, and if K is greater than 1, we get AND nodes. Okay, so let us see what happens in the AND OR graphs. Okay, it requires more bookkeeping because as soon as we get a solution to one, we find that one goal has been reached. It doesn't mean that you have solved the problem completely. Okay, you may have found only half a goal. You may have not found the complete goal. Okay, so when you are searching AND nodes, all the AND descendants of a node must be solved to solve the parent node. Okay, it could be that each AND descendant is a subproblem of the overall problem. Whereas in the OR, you could make a choice, either this or this or this. Okay, so that is the difference between the two in the case of and or graphs. So how do we work on and or graphs? So let's say that we have an and or graph like has been shown over here, right? So suppose I take, so this will show that this is a and graph with both G and H together needs to be completed, okay. So if you take each node singly, you find that G, if you look at all the leaf nodes, G is the best node, right, most promising single node, okay. But it's also part of GH, okay, which means G, if you do G, H also needs to be done along with it, okay. So if this is 3 and this is 4, so 4 and 3, 7 plus the cost of the two arcs, okay. So this arc will cost 9, right. Now another thing is that you also have an AND node here, right. So if you do G and H, you also need to do I and J, okay. So when you do D and H and I and J, then only this will be complete, right. So what you need to do in this case is you have to see from the root node and see which is the most promising node at any point in time and choose that node for expansion. Okay, so what you do is you backtrack from here. So we have 10 and 15 here, so that will be, this node is 27, okay, and this is 9, but again we have an AND node here, so this would be 27 plus 9 plus the two nodes here, so this would be 38, and this node, okay, because this is 10 and 5, okay, 15, you get 17 here, right, and this would be 18. So this path from A has a value of 18 and this one has a value of 38. So this is the most promising node to expand, okay. So when you choose to expand this node, then you can choose either E or F to expand at a particular point in time, and since E has a smaller value, you may choose to expand E at a particular point in time. So at every point in time when you expand E, you get nodes, and again the most promising node may change, right, and you have to choose that. So let us see an example of this. So what you have to do is traverse the graph starting at the initial node and follow the current best path and accumulate the nodes on that path which have not yet been expanded. So you pick one of those expanded nodes and expand it, okay. When you add its successor and compute the value of those nodes, right, then what happens is that the current best path will change, okay. So you have to propagate the changes backwards through the graph and see which is the new current best path and choose a node on that current best path to expand, okay. So let us see an example here. So I have A here and I have expanded A and I get B, C and D, where B and C are AND nodes, right. So what would be the value here? The value of this node will be 5 plus 1, 6, okay. So whereas the value of this path will be 4 and 3, 7 and 9, okay. So obviously you will choose this one to expand. So if you are choosing this one to expand, this path, you have to choose D and expand it, okay. So we choose D and we have expanded. So we get here again an AND node. So 4 and 4, 8 and 2, 10. So this will be 10. So this will have a value of 11, okay, whereas this has a value of 9. So at this point in time, this is the most promising path. So since this is the most promising path, we decide to take B and expand B, right. So when we expand B, we get G and H with 5 and 7. So since they are OR nodes, this will have a value of 6, okay. So this will be 6 plus 4, 10 and 2. So this will have a value of 12, whereas this has a value of 10 plus 1, 11. So this would be the next most promising path. So you take this path and choose to expand this node next. Okay, so this is how you have to work on and or graphs, which is a little different from the or graphs we studied up to this point in time basically. Okay, so let us look at constraint satisfaction problems. So what is the constraint satisfaction problems? You have some constraints in the problem and those constraints will make it easier to find a solution because it removes a part of the search space because of the constraints that it has. Okay, an example is, like I said, the cryptarithmetic problem. So in the cryptarithmetic problem, you have constraints like uh, each letter should be associated with a number.
Okay, let's delve into constraints in selection problem.
But it should be unique, right? So each letter should have a unique number associated with it, and there will also be a range in which these numbers should be, etc. So all these constraints, if you put together, okay, you find that it brings down the search space in cryptarithmetic problems. Okay, so you also have other cryptarithmetic problems like the map coloring problem. Okay, so here you have a map coloring problem. So here what happens is you have the various states. Okay, those are the variables that we have, the various states, and the colors. Okay, we have a set of colors. Here we have pink, orange, green, yellow. Okay, and the constraint is that no two adjacent regions can have the same color. Okay, so there has to be a difference in color between adjacent regions. Okay, so this can be also used and like a constraint satisfaction problem. Other similar problems to map coloring is like final exam scheduling, Sudoku. In n-queens problem also we have constraints. So you can look at it as a constraint satisfaction problem, just like we did in the earlier thing. Okay, this is the n-queens problem. So this actually gives you a solution actually to the n-queens problem. So you can look at it like a constraint satisfaction problem. Another is the job scheduling problem where you have a set of jobs with deadlines and resource constraints. And the goal is to find a schedule, okay, which optimizes the profit. And you have deadlines which also form the constraints. And resource constraints can be represented as in the form of inequalities, right? The resource, some resource you have is less than some amount, etc. And you need to find a schedule which you can do using the constraint satisfaction problem. So let us look at the constraint satisfaction problem from the view of the cryptarithmetic problem. Okay, so let us see what happens, how do we formulate a constraint satisfaction problem. So it consists of three components, x, d and c. X is the set of variables, right? For example, in the cryptarithmetic problem, it is the alphabets, the letters that we use, okay? Those are the variables. And d is the set of domains d1 to dn. So each of the variables will be having a domain, okay? So it varies in a particular range, the values of that, okay? And C is the set of constraints that specify allowable combination of values, okay? So suppose I take D1 or DI, okay? DI will consist of a set of values V1, V2, etc., okay? Which are allowable values which Xi can take, okay? And each constraint consists of scope and rel, where scope is a tuple of variables that participate in the constraint and rel is the relation between those variables, right? Okay, so all these together form what is called the constraint satisfaction problem. So how do we solve the constraint satisfaction problem? Okay. So what you need to do is that you need to assign values to each of the variables. Okay, so for example, we have x1, x2, x3. So each of them you have to associate a value which is there in the domain, okay. So maybe xi equals vi, xj equals vj, etc. Okay. Now you may find that as assignment violates some constraint, okay. So as soon as it violates a constraint, it is inconsistent or it is not a legal assignment, okay. If it does not violate any constraint, okay, it's a legal assignment. So once you find a legal assignment to all the variables v1, v2, etc., then your job is done, right, and you get a complete assignment, okay. A complete assignment is one in which every variable is assigned and the solution to the CSP is a consistent complete assignment, okay. And a partial assignment is one that is assigned values to some of the variables but not to the other variables, right. So CSP satisfies some additional structural properties, okay. So each value has a domain and its own, and the values only occur within that domain, okay. And what is the initial state? Initial state is one where all the variables are unassigned, okay. And operators will assign a value. So what are the operators that we have? It assigns a value to a variable from the set of possible values, okay. That is what it is, okay. And what is the maximum, what we are going to use is depth first search, okay. So what is the maximum depth of the tree? It's equal to the number of variables, okay, because in each depth or in each level you are going to assign one value of one variable, okay. So the maximum depth will be equal to the number of variables that you have, okay. Additionally, you can do, once you come and you find that some value which you have assigned actually violates a constraint, it backtracks and tries some other assignment, okay. And forward checking can also be done every time a variable is instantiated, okay. So you have already instantiated that this variable takes this value, okay. Then what you can do is forward checking deletes from the domain of all the other variables that particular value, okay. So that the domain reduces and it becomes easier to find the overall assignment, okay. So here we have like send plus more equal to money, right. So what we need to do is we have to assign a number between 0 and 9 to all these letters, right. So what is S, what is E, etc. Okay. So what happens is generally what you need to do first here is that suppose I take D plus C, it's possible you are getting a value here and you get a carry, right. So we have to have C1, C2, C3, three more variables we are putting there, okay. So those are the carries and the carry can be any value between 1 and 9, right. Now if you analyze this, okay, you will find that some variables will get instantiated. For example, here analysis has told me that m is equal to, m can be only 1, okay, s can be only 8 or 9, etc., right. So once, and o is equal to 0, etc. Okay, so you find that with some analysis, some of the variables can be fixed, okay. So once you have fixed those variables, the other variables, you can see what is the domain, okay. For example, okay, m equals 1, o equals 0, etc. So some of the variables are fixed. After that, suppose you take the variable e, okay, you can say, okay, I am taking variable e and the variable e can be anywhere between 0 and 9, okay. If you are doing forward checking, since already 1 and 2 are taken, you can put the value of e between 2 and 9, okay. So suppose I put e equal to 2, okay, then you can fix other values, say r, n, etc., right. Now when you come to the value, say after, you are doing depth first search, so each one by one each variable you are assigning, and if you find there is a violation, it means say r equals 9 is wrong, then you can backtrack to the earlier level and you can check other values of r, etc., right? And you can keep doing this depth first search here, okay, till you are able to find values such that there is no conflict, okay. So what you are doing here is actually depth first search basically, okay. So at this level you are finding E, then here you are finding N, and you say R is 8 or 9, so you have two branches here, etc. Okay, so you are using breadth first search, and what satisfies the, I mean, what makes it easier is the constraints that you have. Because of the constraints that you have, your depth first search doesn't become so complex that you need to search everything from 0 to 9, right? After some time, say for example, since O is 0 and M equals 1, you are not going to check that. And once you have fixed some of the other values, okay, you find that the branches that you are getting at the lower levels will be less, right? You won't have so many branches. So it makes it easier to find the assignment, right? So this is how the cryptarithmetic problem is done. And of course, all the other constraint satisfaction problems are also done in the same way. So we'll stop here at this point, and in the next session we will talk about the informed search, where we use some heuristics to find out the order in which we need to expand the nodes. So that will be changed depending on the heuristics that we use.